In this video, I'm going to start to introduce a special kind of tree known as a red-black tree. And the important part of a red-black tree is that it's a type of tree that's always going to maintain a balanced property. So it's always going to be generally balanced. When we talked about our binary search trees before, we said one of the problems with them was that if we were to have a non-balanced subtree or a non-balanced tree, we could have a pretty bad time complexity where we end up basically with a linked list or linear-based time complexity. So in order to avoid that, we often have these different balanced types of trees, and one type is a red-black tree. With the red-black tree, we do a few modifications to our binary search tree data structure. We start by labeling every single node in the binary search tree with a color, either red or black. And generally, the idea here is that if we maintain these four properties, the tree will remain balanced. So the four properties are that the root is black, every leaf node is black, if a node is red, both of its children are black, and for each node, all the simple paths from a node to a descendant leaf contain the same number of black nodes. To help to clarify this, let me show you an example, and we'll discuss some of the interesting kind of intricacies of a red-black tree. Here is an example that we could have. So starting off, I'm going to define my root, which must be black. And let's say that my root has two children, B and C. And then let's say that these nodes have some children as well. Well, when we're taking a look at our properties, because these two nodes I've chosen as red, their children need to be the color black, right? So we make these black here. And you can see that this tree that I've drawn out generally satisfies each of these different properties, right? The root is black. Each of the different leaf nodes is black. Now, you have to be kind of careful about this. In some cases, people sort of misunderstand what a leaf node is inside of a red-black tree. In our binary search tree, we would have called these nodes, D, E, and F, our leaf nodes. But what the red-black tree does is it does something very interesting. It actually adds to every single tree node a special kind of node when there is no child, known as a nil node. A nil node is basically a node that has no value. It's the representation of none in this tree. And we set each of these nodes to have the color black. And we consider these to be our leaf nodes. So actually, these nodes here are all our leaf nodes, and this node here is our leaf node. There's a lot of different reasons why we do this sort of thing. One of the core reasons that you'll see when we do our implementation is it makes it easier to be able to find our parent node when we reach the end of our tree. So that's one of the key things about this. Also, having these nodes here allows to maintain this property of each leaf node being black in an easier sort of way. And we'll see that in action when we talk about the actual inserts on our red-black tree. So that's something really important to keep in mind, is that we have these nil nodes that are attached to every node when it doesn't have a child. Those nil nodes are considered to have a color of black, and that's how we're generally satisfying this every leaf node is black property, right? We'll see here that the nodes that are red all have black children, so that is as expected. And then for all of our different nodes, if we wanted to get from one node to a leaf node or a descendant leaf, we would be able to traverse the same number of black nodes. So like, for example, if you started at A and you wanted to get to D, you would traverse two black nodes, right? A and D. Similarly, A to E has the same number of black nodes, and A to F have the same number of black nodes. So you see that no matter what, when we start at one node and traverse to a leaf, we always go over the same number of black nodes. There's generally a balance between the red and black colors, and that's generally how we're maintaining the balance of our tree. Now, I will say here that red-black trees have a lot of interesting intricacies to them. When we do insertions and deletions, we're going to see that there are a number of different things that can go wrong inside of this tree, and a number of different ways that we can fix them. So we're going to spend a fair bit of time just discussing the theory around how we actually fix things like insertions, and then we're going to get into the code, because if I just dive into the code immediately, you're going to get lost very quickly, because there's just like a lot of different cases that we need to consider. So this gives you the general idea of what a red-black tree is and the different properties that are associated with it, general idea of what they look like, and we've introduced this idea of a nil node. In the next video, what we're going to do is we're going to discuss the idea of insertions into the red-black tree. So I'm going to discuss how we can insert a node, what sort of things can go wrong, and how we're going to fix those general problems in our insertion. So we'll take a look at it in the next video. Thanks so much for watching. I'll see you in the next one.